Hi everyone, this is Worksheet 6.1, Maximum Non-Expansive Work and Internal Pressure. And this is to finish up our discussion on the maximum amount of work that can be done by a system. And recall that last time what I told you was that a small change in the Helmholtz free energy must be less than or equal to the amount of work that you could get out of the system for a given process that corresponds to that change in the Helmholtz free energy. And now we're going to see about what the Gibbs free energy has to do with how much work we can get out of the system. And that's going to involve splitting the work into pressure volume work, that's also called expansive work, and non-expansive work. An example of that might be forcing a current through a wire, say, if the system is a battery or something. Another example might be stretching an elastic surface, perhaps, or a spring or something. All right, and so therefore, in that case, the small change in work is going to be equal to the negative pressure times that small change in volume. And again, we're assuming that this process is reversible. That's why you don't see external pressure in there, plus this change in non-expansive work right there. Okay, so if that's true, then what that means is that the change in internal energy equals the work plus the heat. But we can say that this just equals negative PdV, the expansive work, plus the non-expansive work, plus dQ. And now we can rearrange this algebraically and say that du plus pdv minus dw non-expansive, I just subtracted both of these things and brought them over to the other side, is going to be less than or equal to TdS. And I used the Clausius inequality to relate those two variables right there. And then I can further manipulate this algebraically by subtracting TdS from both sides and adding the non-expansive work, to both sides. There should be a line there, non-expansive. And then what I get is that du plus pdv minus tds is less than or equal to the non-expansive work. And if you look back at your notes, you'll realize that this right here equals enthalpy, and this whole thing right here is a small change in the Gibbs free energy. And so what that implies is that the maximum amount of non-expansive work that you could get out of a system is limited by the Gibbs free energy. So therefore, dg is going to be less than or equal to that small change in non-expansive work. Make this look a little bit nicer here. There we go. Why is it less than that? Well, because if you want to get work out of a system, it's going to be negative, so therefore there's sort of a lower limit to the amount of work that you could get out of the system, and that lower limit is the Gibbs free energy, and that's going to be an equality under reversible conditions. All right, and so the last thing on this side of the sheet is if only pressure volume work is done, then there is no expansive work, and the condition for spontaneity becomes that the Gibbs free energy must be less than or equal to 0 for something to happen spontaneously. And that really ought to be it really ought to be less than 0 for it to be spontaneous, because if it equals 0, then the system's at equilibrium, and you might as well just classify that as non-spontaneous. Okay, here we are now on the other side of the worksheet, where we're going to talk about the internal pressure, and we're actually going to finally get to see where it comes from. Now, if you recall what the internal pressure is it's a definition of the change in internal energy with respect to volume at constant temperature. And I just told you in chapter 2, I believe, that it's equal to T times the change in pressure with respect to T at constant volume minus T. And I didn't tell you why that was true, I just gave it to you. And now, today, you're going to get to see where it came from. And in order to see where it came from, we have to start from du equaling T ds minus P dV. And we saw that that was true in class. And the next step is going to be to divide everything by dV at constant T. And so now that's going to become du dV at constant T. So see here, why don't I just actually make that note over here, dividing everything by dV at constant T. And what that's going to give us is du over dV at constant T. T ds dV at constant T minus P dV divided by dV, that just becomes 1, so then the P is just left there all by itself. Hopefully you recognize that that expression is beginning to resemble the expression that we have up at the top for the internal pressure. And now the next step is to obtain the Maxwell relation, and the thermodynamic variable, the thermodynamic function rather, that we're going to use to get this Maxwell relation is the Helmholtz free energy, dA. And so I'm going to make a total differential now for A, Helmholtz free energy, which, if you recall, has the natural variables T and V. So I've got partial A, partial T at constant V times the small change in temperature, plus the partial A, partial V at constant T times the small change in V. And this, according to the definition of the Helmholtz free energy, is the negative entropy, and this right here is the negative pressure. So really what this equals is negative S dt minus P dV. And that should look familiar from the Legendre transforms that we did in class. All right, now the first step will be to get the derivative of S with respect to V at constant T, because that's what we have right up here. And now the next step is going to equate this to a derivative with respect to V of negative derivative of A with respect to T at constant V, and the whole thing there at constant T. But we know that we can just flip around the order of derivatives, and we can also pull that negative sign out in front. That doesn't really make any difference. So this becomes negative partial with respect to T of the partial of A with respect to V at constant T, and then that whole thing there is at constant V. And this right here is the negative pressure, and those negatives are going to just cancel out, and so what this becomes is the partial of P with respect to T at constant V. All right, so now we can replace that that derivative of entropy with respect to volume, and the expression that we get finally is that the partial of U with respect to V at constant T is equal to T partial of P with respect to T at constant V minus P. And I really love this example to show the nature of thermodynamics, which is just a series of connections between all of these variables. And that's where the power of thermodynamics lies, is that it makes all of these connections.